In previous lecture, we have seen the design and analysis of RF absorber. In continuation to the previous lecture, now we will see the hardware part of absorber as well as how we can make application of RF absorber for ambient or intended energy harvesting applications, so that the smart city, smart home, healthcare sensors can be converted into self sustainable sensors. It means they will no more require the batteries for power supply or the inbuilt power supply. They will be getting the power supply from ambient or radio frequency which is available in the environment. For that, we discussed in the last lecture that we make use of metamaterial so that the DNG materials or DNG characteristics can be obtained. In today's class, we will see that there are two types of structure. One is rectangular, another is circular. Rings are being indicated in this slide, and these are known as split ring resonator. By incorporating these structures, we will be able to alter permeability and permittivity characteristics of the materials, and they will behave to alter the phase change of incident electromagnetic wave. Now, for example, as seen in figure A, it is rectangular ring resonator or square ring resonator. In figure B, we see that it is a circular ring resonator where we see that the microstrip line is turned into a particular pattern, and in between there is a gap, desired gap is left, so that we can get the frequency response as 1 upon 2 pi root under root LC. So by this way, by controlling length of microstrip line, width of microstrip line at the gap, we will be able to get a metamaterial characteristics at a particular frequency. Now, the same thing has been represented in this particular slide, where more than one rings are being used. It means the response of ring resonator will be at two different frequencies. Reason being, two different setup of the architecture has been embedded on one PCB. It means they will be resonant at two different frequencies. So on similar pattern, we can develop ring resonator for one frequency, for tune to two frequency, tune to three frequency, and then we can harvest energy in multiband, so that high amount of DC voltage can be produced. Not only with the help of multiband and combiner, we can also alter or increase or enhance the DC voltage by adopting the voltage multiplier circuit that we will see in the subsequent slides. So as seen in the architecture, it is a three-layer architecture. The bottom is ground plane, and above ground plane there is a substrate which has the permittivity characteristics as ER is equal to ER dash minus J ER double dash, and on top there is a frequency selective surface of metallic in nature. Generally, these are made up of copper, gold, graphene, depending on the frequency of usage. If we go for terahertz frequency, we generally use gold and graphene as a material to convert FSS of that particular material. If we go at microwave frequency, the FSS material is generally copper. And we see here the equivalent circuit of the PCB is being represented here at Z0, ZT, ZI, Z ground, ZFSS and D. So here Z0 represents characteristic impedance, ZT represents total impedance, ZI represents input impedance, ZFSS represent the metamaterial impedance, and epsilon r is the permittivity characteristics of the dielectric material. GND represents the ground plane impedance, and in total if we see, the equation of absorber becomes is equal to 1 minus S11 mod whole square minus S21 mod whole square, which represents that the absorption of absorber will be depending on two crucial parameters. One is reflection coefficient, another is transmission coefficient. Generally, because of ground plane is being placed at the bottom, so S21 will be 0. But if we carry out matching of absorber equal to free space impedance, so minimum reflections are being achieved here. So S11 will be as minimum as possible or equal to 0 if it is perfectly matched, but that does not take place in reality. Here we see that S11 formulation will be ZT minus Z0 upon ZT plus Z0, and ZT is the total impedance of the absorber, which becomes ZFSS parallel to ZD, or ZFS parallel to ZD plus Z ground plane. Now we need to work out for Zn so that ZT become 377 ohm. From this formulation we are able to see that Zn will be Z0 in bracket Z0 plus ZL tan hyperbolic beta L upon ZL plus Z0 tan H beta L, where L is generally lambda by 4, so that we can bring it Zn to 377 ohm, or total impedance of the absorber which is designed will be equal to 377 ohm. Now we want to bring the Zn is equal to ZL, so that we say that now it is perfectly matched. In this formulation, the input impedance at surface of observer can also be written as Zn is equal to Z0 Zd plus Z0 tan hyperbolic gamma t upon Z0 plus Zd tan hyperbolic gamma t. So this is the formulation used for input impedance. Similarly, for characteristic impedance, that is Z0, can be written as mu upon epsilon, or mu naught mu r upon mu naught mu r under root, or in simplified form it can be equal to 377 ohm. Or you can say the free space impedance into mu r upon under root epsilon r will be the Z0. It means to bring the total impedance Z0, Zn, all parameters we need to tune. Now the Z material is equal to Z0 tan hyperbolic gamma d. So Z material can also be represented as ZA under root mu r upon epsilon r tan hyperbolic j omega under root mu epsilon t, where we can say ZA is free space impedance and epsilon r is relative. So the thickness of dielectric material, the material used to design SRR, the material used to design ground plane, these all matters. Ultimately, the total impedance of Z ground, dielectric material and FSS must be equal to free space impedance. If it happens, then we will say the incident waves will be captured without any hesitation, or we can say it is in perfectly matched condition. Now, not going more in detail about these formulations, I'll need to say that we measure reflection coefficient of absorber as we have seen in the simulations. So generally we feel that the matched, if the impedance is properly matched, then the S11 or reflection coefficient of measured result will be equal to the simulated result. Of course, if we have designed a absorber at 2.4 gigahertz as well as at 1.6 gigahertz, where you will see that these are the three SRR which correspond to 2.4 gigahertz, where we find that microstrip line length is L and in between there is a gap. This gap corresponds to the capacitance formed. So the total structure of each ring will have a particle value of C and particle value of L. So these three are coupled to each other. So these three structures of ring resonator or SRR or square ring resonators, or you can say the rectangular ring resonators, are designed to operate at 2.4 gigahertz. These are the bottom layers, and if we see on top layers, these are square or rectangular ring resonators. They are having larger size as compared to the bottom ring resonators. It means larger size will correspond to low frequency and smaller size will correspond to higher frequency. So 2.4 gigahertz, these all three ring resonators are there, and larger size 1.6 gigahertz, these all three ring resonators are there. They are coupled with capacitive coupling. Similarly, these three are coupled with capacitive coupling. Now if we see the center part, this is FR4. So permittivity of this FR4 is 4.7. Now if we see here the back side of the RF observer, this is ground plane. So in total, what we can see S11 of the complete structure. If it is perfectly matched, the S11 must be the minimum or minus 10 dBm or say resonant at two different frequencies. One is at 2.4 gigahertz, another is 1.6 gigahertz. Now the incident wave hits to this, so these are the charge carriers get accumulated at this gap. This is capacitor, and if these are perfectly matched, the charge carrier will constitute a surface current, will enter into the substrate, will form a loop current, and will get reflected from the ground plane. So thus a parallel and anti-parallel current constitution will take place, and here you see that the absorber part will offer a dielectric loss and the conducting part will offer a ohmic loss. So the combination of ohmic loss and dielectric loss will constitute the absorption. So total absorption will depend on all these parameters. One is the structure, another is the dielectric material, and bottom the ground plane. So the total structure must be responsible for the total loss or absorption coefficient. Now these are metamaterial absorbers. Reason being, the structure is specifically designed so that the incident wave phase angle is being changed by these structures. Or we can say that in place of reflections, these are routed towards the substrate, and they are being again to and fro or in both way. The EM waves travel inside the dielectric, and the travel movement will constitute a dielectric loss. So this is all about the RF absorber. Now these S11 as well as absorption parameter can be measured with the help of vector network analyzer. Further, if we place the diodes in between the gap, these three gaps are there, so we can place Schottky diodes in these gaps, and then these diodes will accumulate the charge carrier, and then we can connect these diodes to a rectifier circuit using double or quadruple configurations, and we can connect a load. So the DC voltage, this is AC voltage available across the diodes. So with the help of rectifier, either a doubler circuit or voltage multiplier, quadruple circuit, we will be able to get this AC voltage into DC voltage, and the DC voltage will be sufficient enough to cater to the IoT devices. So this way the ambient energy can be converted into corresponding low DC voltage. That's all for the today's lecture. Thank you.